All right, this is going to be a video that will go over problems involving the central limit theorem. And these were assigned for my students in my statistics class at Foothill College for Monday and Wednesday. That was due on February 25th. These are from the chapter 6.3 in the book that is used at Foothill. So we're first of all going to review the central limit theorem. Which tells us that the distribution of x bars is normally distributed with a mean that's approximately equal to the mean of the is equal to the mean of the population, and a standard deviation called the standard error of sigma, the population standard deviation, divided by the square root of n. Now this is the distribution of x bars when the standard deviation of the population is known. Now something that's related to this is the sampling distribution of p hats. And the sampling distribution of p hats is also normal, and it has a mean that's equal to the population proportion and a standard error equal to the square root of p times q divided by n. And that will come up later on as we start studying inferences based upon the normal distribution. So our first problem, I will read it to you. It says, suppose that we had a distribution with a mean of 15 and a standard deviation of 14. And if we had a random sample of size 49 with that mean and that standard deviation, we would want to find the probability of being between the means being between 15 and 17. So we're being told that the x bars or the x's are distributed in some way that we're not really sure of. Let's see. Yeah, we're not told how exactly. And we have a mean of 15 and a standard deviation of 14. So these are the things that we're told. Now our first question is to find out what the probability of having an average then between 15 and 17 inclusively for a sample of size n equals 49. Now, because the sample size is greater than 30, the central limit theorem applies and tells us that the x bars are then distributed normally. So if we know n is greater than 30, we automatically know that this is normally distributed with a mean of this and a standard deviation, called the standard error, of the standard deviation divided by the square root of the sample size. So we're going to use that fact in order to find this probability. So we're going to find this probability by standardizing. We're going to take our random variable, we're going to minus the mean, which our mean is told to us to be 15. We're going to divide it by the standard deviation of the distribution. Well, this is what we have as a random variable, and our random variable's x bars are distributed normally with this mean and this standard error. So we have 14 divided by the square root of 49. And so what we have is a z-value there. We'll standardize this, so I'll write that using notation. And then we'll do the same thing with our 17. So 17 minus the mean divided by the standard error as well. And so now what we have is we have a value equaling 0 on the left. We have standardized this, so we now have a z-score, which we can use our standard normal table to find. And then we have 4 divided by 14. So I have 17 minus 5, or 17 minus 15, which is 2. And then the 2 in the denominator down here, that's not a 2, sorry, that's a 7. The 7 down here in the denominator, that is going to come up and multiply by the numerator here and divide by this. So we really have a 2 divided by a 2 is another way of looking at this. But I like to show my students that we do want to take a look at this value here, which would just be for a normal random variable x, and then say, oh, well, that's actually 7 times larger than that value, because that puts a relationship between the distribution of just the x's versus the distribution of x bars, and it shows us how much wider ranges we can when we get when we include the mean, and how much smaller probabilities we get when we are not including the mean. So that's kind of the way that I like to show those. At any rate, once you make this computation, we end up with a positive 1 over here. So now we're finding this probability. Well, this probability, remember, looks like the probability of being between 0, and here's our approximately 1 there. It's a little bit further out than that, but it doesn't really matter. That's approximately what I'm looking for. So I'm going to be finding the half the distribution here minus what's in the tail over here. And I'm going to find what's in the tail over there by looking in a negative z-table, because that's what I have here, and I'm going to find that by looking for less than a negative 1. And so I go over to my table, I look for a negative 1, and I find this value right here, 15.87. So I have 0.5 minus 0.1587, and I'm going to make that subtraction, and that's going to give me my value. So 0.5 minus 0.1587, and we get 0.3413, and that will be my probability here. Now my next question says, if the random sample of size 64 is drawn, find mean and the standard error and the probability that our average value is between those two. So I'm going to go ahead and I'm going to change colors. So here on part B, I have exactly the same question that I had up here, so I'm just going to highlight that so I don't have to write it again. But this time, my x bars are distributed with the mean of 15, normally, with the mean of 15 and a standard error of 14 divided by the square root of 36, because my sample size is 36 this go around. So that changes the standard error. The mean still stays the same. We're still going to apply the central limit theorem because we have a sample of size over 30, and even though we don't know the original distribution, the central limit theorem will still apply. So this time around I have 15 minus 15 divided by, and this time it's 14 divided by 6, which still doesn't matter on that side since how it's still 0, and my x minus my mean divided by my x bars minus my mean divided by my standard error, and then my 17 minus my 15, and this time around divided by 14, and then divided by 6. So in other words, this 17 minus 15 divided by 14, that's the same value up there. And instead of multiplying it times 7, I'm going to end up multiplying it by 6. So my value, in other words, is not going to be as far out here in the tail as it was at 1. And so I'm going to see a smaller value. So let's go ahead and do that. 17 minus 15 divided by 14, and then multiplied by 6. And that gives us a 0.85. And so you see that it isn't as far out in the tail as it was before. It's more like right in here. We have a smaller area. So we have 0 is less than or equal to a z. Standard normal is less than or equal to approximately. Now I have you round these to two decimal places, because that way no matter if you're using a table or you're using a calculator, everybody gets the exact same value. And again, we're going to be doing 0.5, half the distribution, right? Half the distribution minus what's over in this tail over here, which is the same as if it was over in that tail there, which is minus the probability that a z is less than a negative 0.86. And so we'll look up that probability in the tail and get our probability as our final answer. So this is 0.5 minus, and 0.86, 0.8, and then 0.6 right here, and we have 0.1949. So 0.1949. So 0.5 minus 0.1949, which gives us 0.3051. 0.3051. and that's our probability. Now the last part of this question said, why should you expect the probability in part B to be higher than that in part A? Well, the probability in probability in part B to be higher than the probability in part A. Oh, I didn't do the problem correctly. It was 64, it wasn't 36. So with 64, yes, it would be indeed higher, because with 64, sorry about that, I misread the problem. It was 64 here instead. Instead of being 66, this would be an 8. So this number here got multiplied by 8 instead of 6, which puts it at a further out here. You see the probability increases, and so at this, let's see, we would have 17 minus 15 divided by 14 times 8, which gives us 1.14 this time. Sorry about that. So this is 1.14. And this one being a negative 1.14, right? And then if we look up negative 1.14 here, we get this value right here, and that's 1271, and the difference between those, that would be 0.3729. And the difference between those, of course, you see this one is larger than this one. And we actually have an even better comparison here, because we saw when we divided by 6 here versus 7 there, we had less probability. With the 6, the division by 6, which is a smaller sample size still than we have up here. And when we have a larger sample size, we have even larger probability. What's happening is that the jitter is less when we have a larger sample size. So the probabilities of being in a range that includes the mean is much more likely, right? Because the values jitter less on average away from the mean. So you're going to have much better probabilities. So that was the first question that was asked from our set of exercises out of section 6.3. Now the second question that was asked out of our section 3 homework, it starts out in the following way. It says, let X be a random variable that represents the white blood cell count per cubic milliliter of whole blood. Assume that X has a distribution that is approximately normal with a mean of 7,500 and an estimated standard deviation of 1750. A test result of X being less than 3,500 is an indication of leukopenia. This indicates bone marrow depression that may be the result from a viral infection. So this time around, we're told that our X's are distributed, and they're told this time that they're approximately normal. So the central limit theorem will apply no matter what sample size we have. We don't have to have that n greater than 30 that we normally have to have. And our mean here is 7,500, and our standard deviation is 1750, and we have these in white blood cell count in cubic milliliters, so milliliters cubed, and that's blood counts. So we're going to go ahead and we're going to answer the questions based upon this. It says, what is the probability that on a single test X is less than 3,500? So the probability that on a single test that X is less than 3,500. So that's what we're looking at on that one. The second question says, suppose that a doctor uses the average of 2 tests. So we're looking at a sample average this time, an X bar, and we want to know the probability in that 2 is less than 3,500. And so this time our X bars are distributed normally with the same sample mean we saw before, but now a standard error of the standard deviation of the population divided by the square root of our sample size 2.